So this word-to-vec has two problems that I will explain. That's why we use negative sampling techniques in this lecture, and also hierarchical softmax in the next lecture. Hierarchical softmax. This hierarchical softmax is different from the softmax that you know. It's a different thing. But in this lecture, I will talk about negative sampling. So first, I will explain the basics of word-to-vec. For those people who are not familiar with this topic, of course, I've explained word-to-vec in my channel in NLP, Natural Language Processing. But here, I want to explain it with more details and see it how we can implement it in Python. So it all began in 2013 with these great scholars, efficient estimation of word representation. We want to assign a vector to a word. So this word vector, this token, this word, were represented by a high-dimensional vector. So there are two approaches: continuous bag of words and continuous skipgram. And as you see, the continuous bag of words, you give the context. For example, in the sentence, machine learning is a method of data analysis and so on. Machine learning, a method, these are the words that are surrounding is. And is should be in your output. In this way, you don't need any label. You just need to know what is the center word, what is the surrounding, and you just train it. In this way, you can learn what is the vector representation of any word you like in your sentences in your texts. So the continuous bag of words, you give context to the model, and what you get is the middle word. But in skipgram, it is the opposite. You give the center words, and what you receive is the context words. And for example, at first what you give to the model is the one-hot representation. For example, everywhere it is 0 except 1 at the index of your of the word that you are giving it. So you give the center word, and what you receive is the context words. And it's a word, so it's a probability that each word has. What is the probability of each word has in the context words, surrounding words of the center word. So this is a continuous skipgram model. So if you give is to the model, then the context words are machine learning and method A and method and so on. So you see, it's pretty obvious that you give the middle word, and what you get is the probabilities of the context words. For example, here you give this one-hot vector for passes, and this is the probability that you receive for the context around it. For example, the and who. And why not using Jensen? Because it has already implemented all of these things. Because if you want a standard model with standard ways like simple hierarchical softmax and the negative sampling, the standard version of that, of course, then you can use Jensen. But if you want to have your own complex ideas of hierarchical softmax and more advanced way of negative sampling and even different paradigms in order to avoid the problem that I will talk about, then you should implement it yourself in PyTorch. So if that's the case, that you want just a simple model in order to do the already implemented, already proposed ideas in word2vec, use Gensim. So Gensim, you import the word2vec and you give model, but it has some parameters. For example, mean count here is a parameter, mean count. The default is 5. It is the minimum count of words to consider. For example, less than this count is ignored. The other important parameter is the size. For example, have you seen the the file glove 100D is about 1 gigabyte. So 100D, it means the dimension of each vector is 100 dimension. So here the default for GenSim is 100. You can change it to anything you want. You can reduce it because I don't like cursive dimensionality. So please use, for example, 30 at most, or 10 or 20. But if you have large vocabulary, the standard thing that it teach you in the school is to use the things. So you should use it. But there are other parameters as well, such as workers. So if you just use workers, you can already use that multi-threading that is implemented. You can use 3 threads in a multi-threaded fashion, so it's very fast. You can take advantage of multi-threading. And when SG is 0, it means continuous bag of words. When it is 1, it is a scriptgram. And also the window is usually set to 5. That's why for GenSim the default is 5. And so we give the sentences, this one, the sentence, the other sentences, and you receive what you receive after saving the module. Then when you load it, you have all the vectors of all words in these sentences. So the problem is that the softmax is expensive when you want to use it in Word2Vec. That's why we have 2 methods, either negative sampling that I will explain in this lecture, but in the next lecture I will talk about hierarchical softmax. It's really beautiful piece of art. It's an art, it's not science, it's art. And so you can use continuous bag of words or skipgram. Each of them could be implemented by either negative sampling or higher, because you have a big problem. Your denominator is huge. You have V computations are needed to get the normalization factor. So it takes a long time. So that's why we should create some methods. That's why they created negative sampling and hierarchical softmax. And so the negative sampling is very easy. You just get some of these a subset of these, and you will see here for loss you need a negative loss, you need a positive loss here because you want to increase this likelihood, and what you want is, so you get here is the batch matrix multiplier of negative V, and embedding U here and embedding V negative. So you get the negative score. This is the negative score. You want this word with the surrounding to be, so the positive things are the likelihood will become very harsh, but when there is another word that is very far away, this is negative distance. You want it to be, this distance to be as much as possible. That's why in training these, you can use this negative loss idea, negative dot product of uj and vc. So this is the negative, but at the same time you want to two words that are close to each other to have a very small to have a positive score. That's why this context should be around the center word. That's why this is the positive score. And you see, it's very easy. You just sum the negative score, and this is the negative score, this is the positive score, and then you add them up. So first you should clamp it. Clamp is here from -10 to 10. It means that this is you cut it from -10 to 10. And PyTorch implementation of skipgram models like this. We use log sigmoid. And the forward, as I said, you have the positive score, negative score, and you add the positive score and negative score. This is what should give you the return of the forward. Because you know the word in the center, the context, you should also know the negative sample, because negative is the thing that is far away. It should be far away. Otherwise, it doesn't make sense. And what you receive is the mean of this score. Because you need this in order to calculate the loss and optimize it in this boilerplate prot code that we always write. Because for any iteration, you have some batches and you give it to scheduler. I always use a scheduler because I don't want my learning rate to be fixed. And then the rest of it is very standard. You use zero grad and then lost that backward, and you get lost from that forward that I told you. You see, you added these and this loss model in the previous slide. So you get this and you receive the loss. And using loss, you can backpropagate and tune your model. And finally, if it is good, if this is the training loss and this is the validation loss. If it is like this, it is nice. You keep it, save it. But if your training loss is like this, but if your validation loss is getting like this, it is not good. It is oscillating. It is overfitting. So your model is not overfitting. It is not generalizing well. Do not save it. So this is really nice. If this happens, it means your model is converged, and now you can write your own paper and will be published because it is converged. And that's it for implementation of PyTorch, implementation of Word2Vec in PyTorch.